This is number 2 under area volume FRQs. This is another calculator active problem. We have region R that's created by f of x, that's the curve here, the polynomial, and the horizontal line y equals 4. That encloses that region R that we see there. For part A, it says find the volume of the solid generated when R is rotated about the horizontal line y equals -2. So we're going to rotate this around the line y equals -2. I drew that here, and we can see that there is an obvious gap between the shaded region and the axis of revolution. So we know that because of the gap, there's going to be a hole, and we got to subtract out the hole. That means we have to go through washer method, and it's not going to be this method. So washer method for volume. So in order to continue with washer method, we'll have to find two radius. One radius that's going to extend from the axis of revolution all the way to the furthest boundary of the shaded region. And then little r is going to extend from the axis to the closer of the two boundaries of the shaded region. So once we have our big R and little r, we can obviously tell big R is longer in length than little r. So now we're going to do top minus bottom, since we're dealing with vertical. We're dealing with a vertical radius. So the top of big radius is hitting y equals 4, so 4 comes first. So it's always top minus bottom, top minus, and then the bottom is sitting at -2, so 4 minus -2. Careful to keep track of your two negatives there. 4 minus -2, we get 4 plus 2, which is 6. And then for little r, top minus bottom, the top function is sitting on the curve, so that's the polynomial here, minus the axis of revolution, so minus -2, which is plus 2. Combined like terms, we get x to the 4th minus 2.3x to the 6th plus 6. Our bounds are still going to be in terms of x, so from 0 to 2.3, which we can find if we use second trace intersect to find that intersection between the graph y equals 4 and the polynomial. Okay, which could give us 2.3. So the formula for washer method is big radius squared minus little radius squared. And we can enter all this in the calculator to evaluate, and we're going to get a volume of 98.868. For part B, region R is the base of a solid. Each cross-section is perpendicular to the x-axis. So let's think about this. X-axis is horizontal. So perpendicular to horizontal must be vertical. So we know that our base length is going to be vertically drawn. So we do top minus bottom. The top of my base length is sitting at the 4. The bottom is sitting at the polynomial. Careful that you put parentheses around your polynomial as a way to remind you that the negative has to distribute through. Once the negative distributes through, the 4's cancel out. We're left with negative x to the 4th plus 2.3x cubed. That's our base length. That's our base expression. But we have to put it into some area formula because we're building a specific shape on top of this, this flat surface. And the shape that we're building is an isosceles right triangle with a leg on the base. So that formula is 1/2 base squared. Isosceles right triangle with a leg on a base. So once we have this formula, we're going to adapt this to our specific problem. We put our base expression in for the formula for area. So we have 1/2 negative x to the 4 plus 2.3x cubed quantity squared. We move from our two-dimensional expression to a three-dimensional expression with the integral and dx at the ends. And all this is going to be calculator work, math 9, definite integral. We get 3.574. Okay, part C. The vertical line x equals k divides region R into two regions with equal areas. So we know that x equals k is going to be somewhere between here, somewhere in this region, that will allow R to be split up into equal areas. But we don't have to solve for k, we just have to write an equation that will represent the ability to solve for k. So here's my diagram. Let's say we have x equals k somewhere around this region, and if this is the case, then the definite integral from 0 to k must be equal to the definite integral from k to 2.3. So we allow for that equation there to represent the two equal areas that will be split in half. And for each region, we have top minus bottom. The top function in each region is going to be the linear, it's going to be the y equals 4. And then the bottom is going to be the polynomial. Same thing in the second region, this right region here as well. 4 minus the polynomial. Okay. So that's all we need to do to set that equation up.